being recorded. Okay. So yeah, I think we should start. So thank you very much for coming on a Friday. The attendance is not normally we are more. You have seen it. So today we have a seminar by the visitor Lientur, and he's from Concepción in Chile. He did his graduate studies there, and now he's doing his PhD in Valparaíso. Hey, come. Don't be shy. Don't go away. So today he's going to give us a talk about the Nova shells with MUSE. So I hope you enjoy it, and all yours.
Thank you for the introduction. For you to be here today on this Friday. So this talk is basically my research that I've been doing in my PhD. So I'm working with closed hardware and Smith today in the area of Nova shells. So first sorry. Yeah. So first I would like to introduce myself as Juan mentioned. I'm from Concepción, this beautiful city in Chile. Here I have to visit. Currently I'm doing a PhD in Valparaíso. My area of research is the stellar one, especially focusing on the study of binary stars. Speaking of that, maybe you know, maybe not, but most of the stars in the universe are actually in binaries. This means there are two stars each other, and if they are close enough, they can interact with each other. This will affect the evolution and will give origin to several physical processes that, for us astronomers, are quite interesting to study. I will focus this talk in a particular group of binaries called cataclysmic variables. This group of binaries are composed of a low mass star in its main sequence and a quadrupole companion. The quadrupole is always more massive than the low mass, than the main star, and the orbital period in these systems are very low. So this is a histogram of the orbital periods of the cataclysmic variable within a 150 parsec radius from the solar system, and we can see that the orbital periods are in the scale of hours. This means that the approach log is small enough for the main sequence to start to actively transfer matter to the quadrupole companion. How the matter will be accreted in the quadrupole will depend basically on the magnetic field of the quadrupole. If this is non-existent, the matter will be accreted to an accretion disk and eventually to the equator of the star. But if it's not the case, and the magnetic quadrupole has and the quadrupole is magnetic, the accretion will be done to the magnetic axis. And here we can also make the distinction if the magnetic field is strong enough to actually truncate the accretion disk or totally inhibit its existence. Whatever the case be, the response of the quadrupole to the accreted matter will depend on its mass and the mass accretion right here. This diagram is from Cardo et al. And shows what happens with the accreted matter that is accreted. If the system is in this region that is called steady burning, then the accreted hydrogen will immediately burn into helium, effectively increasing the mass of the quadrupole. But if not, and this is below this line that is called the end of the stable, the matter will be accreted until enough matter has been accumulated to the surface to ignite the thermonuclear runaway process. In the case of cataclysmic variables, the mass of distribution of the quadrupole shows a peak at around 7.8 solar masses, while the mass transfer rate of the system is always below 7. So this means that in cataclysmic variables there was always thermonuclear runaway process happens. And how this occurs? So to put it quite simple, basically what I show here in this scheme is the hydrogen, the most outer layer of hydrogen, that is one is accreted. And in the bottom one, because of the change condition of the quadrupole, the hydrogen will start to become more and more degenerate until the point that this critical pressure is reached. When this critical is reached, this hydrogen will ignite to helium via PP change first and later CNO cycle. In the case of quadrupole, they show this relation, the radius and the mass are proportional to each other. So in the end, the amount of matter that is required to ignite to produce the thermonuclear runaway will depend only on the mass of the quadrupole. And the more massive the quadrupole is, the less material is required to ignite to produce this effect that is called the thermonuclear runaway. When this happens, so this thermonuclear runaway happens in terms of minutes, very fast process. And when this happens, all the energy liberated will produce that the outer layers of hydrogen will be expelled into the stellar medium. Together with that, there will be some lack of material from the core. So the ejecta will be enriched with CNO elements from the core. And it's important to mention that this process is energetic enough to expand the outer layers, but not to destroy the fiber, neither the system itself. Therefore, the process will start to occur again and again. This is a recurrent process in cataclysmic variables in time scale of 10 or thousands of years. And understanding the effect that this thermonuclear runaway has, it's important to understand the evolution of these systems. This is just ignite, so the beginning of what we call a nova eruption. But this process and the effect that it can be measured in terms of days and months after the process. And of course, the amount of energy released will be reflected in the brightness of the system. By studying the light curve of the nova eruption, we can see how complex this could be. This is just some examples. So we have this kind of smooth declines that follow the eruption, but this is not usually the usual. You used to have more like complex table like this one. We have some jitters, this multiple maximum, the plateau, dust formations in place. So for us to understand how the nova eruption, the thermonuclear runaway happens, it's important for us to understand what produces all these kind of effects in the light. And for that, the spectroscopical studies are needed. So people have been hunting for novas. When they detect one, they upon the telescope and start to do a spectra for the system. Here we can also see the evolution of the spectrum in function of the times in the nova eruption. So this is a nice example of how the evolution happens. This is V906 Canina. And here some spectra taken days after the eruption. So at the beginning, when the system starts rising its light, we can see the spectrum have this characteristic phase that we call the pseudo-photosphere phase. This is because the ejected material is thick enough to act as a photosphere for the system itself, producing this kind of continuum source. But in the hydrogen alpha buffer is evident the ejection of the material in the form of this piercing buffer. As the time and the day goes by, and the system starts to reach the maximum of the brightness, this pseudo-photosphere starts to become thinner and thinner. So this spectra start to evolve into a more nebular state. And more interesting, in the hydrogen, we can see this dot component start to appear. That is with the piercing buffer overimposed. And many months after the eruption, the system can reach the nebular stage, where the spectrum dominated only by emission lines, no continuum at all. And the hydrogen buffer also doesn't show anymore the piercing buffer, and only show more the dot component that was start to appear at this phase. This is just one example, but this behavior, particularly the hydrogen alpha, has been observed in many systems. So it was proposed by these authors that this is a common phenomenon in the nova eruptions. And they propose that the eruptions occur in this way. So basically, there is at the moment of the eruption, after the thermonuclear runaway, a slow flow of material is ejected from the system, preferentially in the plane of the orbital plane because of the angular momentum conservation. But after that, because the white dwarf is still hot because of the eruption, successive ejection will occur. These successive ejections will be caused by secondary eruptions within the white dwarf or by a continuous wind from it. Eventually, whatever the case will be, the ejected material will be frozen because there will be no more ejection from the system. And we have this particular product shape that we can see here, basically a bipolar outflow with material in the equator of the system and system living in the polar outflows. So this is the theory. Also, this is what we know about the first moments of the eruption, days, months. But this ejected material will continue expanding for months, years, decades, centuries after, until reach the point that we can actually resolve it from our telescope. At this point, when it's resolved, we call them nova cells. And when this reaches there, we're going to study not only we're going to study the geometry, for example, how they expand the evolution. And later, millennia after, we're going to still have some remnants of systems. For example, this one is was the first nova chart with a age estimate in 2000 years. So from China to 2012, we can see there's some remnants of hydrogen, or a system that was originally here. My research, I'm sorry. So why we care about the systems? Because they can act as a diagnostic tool for understanding of the physics of the nova eruptions. By studying the geometry, the kinematics, their abundance, we can compare how these systems react in the present with or what we believe they should, based on the understanding. And they can also serve us to understanding how the material, the expanding material interacts with the stellar medium. This has been the focus of my research, during the last years. And for that, we're focusing mainly in these two stages. So in the stage that the study is already resolved, decades after the eruption. And also a bit in this ancient system where there are thousands of years of old. So there, if I would like to resume my research in just one sentence, would be this. I want to understand how the evolution of these systems as they expand to the ISM. Why? Because there are plenty of questions that we are not sure. For example, we know they should decelerate at some point, but when and how, we don't know. Is the geometry preserved as they expand? If the answer is yes, or the answer is no, we don't know. This is important because if the answer is yes, if it's preserved, it means we will go back in time and extrapolate the geometry now to the geometry at the beginning, to actually compare with the expected geometry based on the spectroscopic information in spectroscopic data. How the luminosity works. As they interact with the ice, it is expected that some shocks happens in the system. And this should increase the luminosity of these cells in, let's say, X-ray, for example, or radio. But this is in theory, but have not been observed to actually happen. Is there something that we can learn from this cataclysmic variable itself, from the white dwarf, from the nova shell itself? It's like from the smoke cloud that are explosive produce, try to learn what was the process itself. And for that, for the study of this system, the most ideal technique is integral field spectroscopy. From a historical point of view, this system has been always observed using narrowband image in hydrogen alpha and long-slit spectroscopy. But in recent years, there has been increasing interest in observing these objects with integral field spectroscopy. This is a technique that combines the best of both image and spectroscopy. To put in summary, what an integral field spectroscopy does is, so we have the image, let's say an example is a galaxy, and we divide this image in several narrow images. For each one, we pass the light to a spectrograph, and we have the different the spectrograph of this part. Then reconstruct the image from this, and you will obtain a data cube where you have an image for each one of the wavelengths that of the spectrograph. This insert in certain sense is similar to what you're doing with JCAS. But instead of using narrowband of 150 angstrom, this one is the scale of 1 angstrom. And in the end, so we obtain a data cube where we have for each wavelength we have an image, and for each pixel we have a spectrum. So we can have the total kinematic and spatial information of an external source. Therefore, an ideal tool for studying nova shells and other kind of external sources. Now, this is the technique. The instrument we are using is MUSE. MUSE is the most powerful spectrograph in the southern hemisphere. It's placed at the BLT Observatory in Paraná, Chile. The wavelengths, so this instrument called the optical wavelength between 470 and 900 nanometers with a spectral resolution of 1.25 angstrom. Or in terms of velocity, say 50 kilometers per second at the wavelength of hydrogen alpha. This is enough for us to study the kinematics of these expanding shells at the velocity are in the order of hundreds of kilometers. And the field of view is also large enough, 1/1 Archimedes, to actually resolve the whole shell in most of the cases. So, our projects consist of an observation of several nova shells with these instruments, MUSE. For that, because we're interested in the evolution of the system, by we I mean Linda, me today, started a project to observe several nova shells that was already imaged many years ago. A nice example of this is R peak. So this is the image of the nova shell of R peak taken in 1995 by Gina O'Brien, 1998. And this system is particularly good for example of the capabilities of the MUSE observing this object because it's one of the closest systems, so only 500 parsecs, and one of the oldest shells, almost 100 years old. This means that the system is close enough and has expanded enough for us to resolve the shell with greater detail. It was already known that in the beginning of the 2000s that the shell is composed of a quadrilateral ring here and some filament leaving the system in what is believed the polar axis. It was the last image in 2000, and since the last year we don't know how this is evolved until we got the MUSE data. So 25 years later, in 2021, we obtained this image of this nova shell. And here we can see how the system has been expanded continuously without the sign of deceleration since the last image. It's also more notorious the different structure that compose the shell. So the quadrilateral ring is the present. We found this cloudy structure that are related to the quadrilateral ring and the polar filament that are leaving the system. For us was a surprise that the system didn't show evidence for inflating with the ISM because it's almost 100 years old. And for many years it was stated that nova shell decelerates with the expansion velocity by half each 65 years. This was stated by Durban in 1987, and since then it's been used by people have been using this value because we know that, as I mentioned, so we know the way this object should decelerate, and it will have to happen when the material drag by the shell is reached. So the material drag by the shell is in similar order than the ejected initial material. So the system will start in the pseudo-Taylor phase, but we don't know exactly when. However, recent studies, so Santa Maria at 2020 and my work in 2024 with RPIC, show that these systems can expand, doesn't show any kind of decelerating during the first system. Basically, invalidating the claim of Durban 87. Still, they should decelerate when we don't know, so we need to continue monitoring these subjects to start to see when this point start to stop following the linear relation and start to reach a plateau. But not only hydrogen alpha. The advantage of MUSE is we can see the shell in different wavelengths. So for the first time, we have look at how the shell looks like in the different wavelengths besides alpha. So we detected the shell in H beta, oxygen 3, the forbidden light, and the forbidden light of N2. We find an interesting difference in the spatial distribution of the forbidden and the low jet insert, with the first ones only visible in the polar part of the systems. This could be because of the difference in intensity of the forbidden, or because of the difference in abundance. And unfortunately, we can now give a conclusion about that with the current data. All possibilities are two, or a combination of all that two. Not only the image, but also the kinematics of the shell can be observed. This shows how the velocity of the predicted velocity of the shell. So basically, we have confirmed the ring nature that was proposed from the image. We can see also the polar nature of the ship. So it's orthogonal basic. So we have a ring and we have orthogonal material. Combine this information, the kinematics, with the spatial that we obtain, we can extract or reconstruct the three-dimensional view of the chart. Reconstruction of the view of the objects in 3D offers a new perspective of the study. And we can rotate and move the chart and the study to our place. Currently, we are basically two groups working this. So one of us is us, and this other group is Martin Guerrero in Granada. So both groups have told that the reconstruction of this 3D offers new possibility of study. But in our case, for that, we assume basically that the chart is expanding free. So with the data was in support this thing, and also is expanding radically. Which is a natural idea, and we don't see why this should not be the case. So we're pretty confident on our chemical reconstruction. By playing a bit with the axis, we can present the same data now in cylindrical coordinates, and here we can see what is the geometry of the equatorial ring, how they expand. We can see that they have this kind of choke or bow choke-like structure, or material here, and interestingly, the oxygen is present only where in these gaps between hydrogen. Again, it could be because of density. So this is this first work we did with RP shows that show first that the ejector test or RP is consistent with what we know and what we expect about the novices, and also show what the capabilities that we can do with the MUSE observing the system. But we also have some other shells in the sample that actually we do not behave as we expect, and this is also quite interesting. I would like to present you the nova shell around B1455 Aquila. This is a young nova eruption. It occurred in 1995, and it's the host of the weirdest shell that we know at the moment. The image of 2019 with GMOS shows the nova shell. The hydrogen alpha shows the circular spherical shape, pretty common, but oxygen does not behave as we expect. Oxygen presents a clear axial asymmetry, where most of the material located in this quadrant of in the southern quadrant of the image, and nothing here. Asymmetries by itself, they are not new. We know a lot of shells with asymmetry, but they are all old systems. And we believe that asymmetry is originated because of the interaction with the ISM. This system is young, 25 years at the time of this observation. And we shouldn't expect that kind of interaction to occur at the time. Also, it's the first time that this kind of asymmetry is actually between the hydrogen and oxygen is observed. What could be the reason behind this? In theory, it could be because of the interaction with the ISM, but we discard this basically because of the age and the fact that the hydrogen doesn't present any kind of asymmetry, or it could be extrinsic. If it's extrinsic, it means if the asymmetry originates during the nova eruption. Also, so the MUSE data that we have also shows that the asymmetry ejecta is weird not only because of its only present in one quadrant, but also because the 3D reconstruction shows that this acts more like an arc. Again, this is even more puzzling because we should expect that this ejecta to behave like a cone or a jet, similar. And instead we have this kind of arc. So we are very confused and we need to provide some answer for the origin. As I mentioned a couple of seconds ago, we believe that the origin for this ejection lies in the eruption itself. And one possibility is that this is evident for a magnetic fiber within the system. Why? Because in a magnetic fiber, the material is accreted to the magnetic axis. And if this is aligned with the orbital plane, the accretion will be equal in both poles, here and here. But if it's not the case and the magnetic axis is misaligned with respect to the orbital plane, it is possible that one of the poles possess more material than the other one, effectively getting an asymmetry in the accretion that could be eventually or could be reflected in asymmetry during the ejection. This is a possibility. However, for this effect is stronger the stronger the field, the magnetic field is in the white dwarf. And currently, we only suspect that the system is magnetic. We don't have strong evidence. So we cannot actually be totally sure that this is the case. More research is needed for us to try to understand this system. That was our work, basically a summary of what we're doing with MUSE regarding these objects. But as I mentioned in the beginning, we also focus in this kind of objects, in the old systems. These old systems are known as the ancient chairs, and they are evidence for a eruption that happened many years ago, and we have not the records. This is important because we can learn about what is the effect of the nova eruption in a system millennia, centuries after its event. There are people that think that the eruption could have an effect on Mars Lampert, for example, for the rate of after the eruption. So the idea with that can be tested if we have enough of these systems. However, we only know there's a few ancient chairs that discovered. And so to draw any kind of conclusion about how this the evolution of the system, we need to have a greater sample. That is the other project. So we were looking for ancient chairs using the omega gamma instrument in the BLT. This instrument is it's an imager. It provides a field of view of 1 square degrees. And so we start to a project of 4 different pointers, each one for one system for a technical variable that we suspect it could happen nothing in the past. So in the end, we have a 40 square degrees observation using the actual hydrogen alpha and RLSS filter to take the image. So unfortunately, the result for this was unsatisfied. So basically, we couldn't detect anything. Even in the system, we know we know the shell exists. We will actually detect it with MUSE here, but in omega gamma, we couldn't detect anything. This is a pity because basically our conclusion is that we couldn't detect anything because we went deep enough. So we cannot draw any kind of conclusion for that. What we did mostly was to develop a series of Python script to reduce the data because omega gamma doesn't have software provided by ESO to reduce data, so we were working on that. And we can provide catalogs in the field. Don't worry, Elena, he will miss you. So, and when I came here, I started thinking, if we're looking, so we failed to using hydrogen alpha in DST and using the SDCS image to subtract the continuum. We're looking at maybe with JPass, this single chart. So, well, you know JPass. So you have these narrow filters, one could be for hydrogen alpha and could be another for the continuum. So we're going to start to looking, well, we could start to looking for this kind of ancient cells in the survey. The only thing that the JPass does is it's actually avoiding the galactic plane, where most of the stars and therefore CVs are present. But still we have plenty of possible systems we will start to look at. The only thing that I'm not sure about this is how deep JPass can go. Here we have so the threshold for detecting was in the order of 10 to the minus 15 erg seconds per second per centimeter square per erg second square. We actually showed that to what have good chances of detecting this kind of ancient channel, we will go towards magnitude bigger. So I don't. All depends if this with JPass we can go as deeper as that. But anyway, I think it could be worth it to check. And start this kind of project with with JPass survey. So I hope I didn't bore you too much. This is a summary of the main ideas of the talk. Basically, no objects are important because they are one piece more from the puzzle that is the study of physics of nova eruptions. MUSE, well, interactive spectroscopy in general, MUSE in particular, are excellent tool to understand to study these objects, as it was shown by my work in RP and other works. And there are some weird kind of chair that before, for example, that will help us to understand better what are the processes that happen during a physical nova eruption. So for your time and your attention, thank you.
Thank you very much, Lientur, for the very nice talk. So, questions? Mohammed?
Thank you very much. So the part you mentioned in the last century that there hasn't been any deceleration.
Yes.
I was trying to look at the speeds, but then you went on. In the plot beside that you had the velocities. No, I think the one before there was one that showed velocity. Yes, that's the next one. Okay, yeah. So the velocities vary a lot from 300 to 700.
So from 200,
And they've
lowest
been,
speed
oh,
is,
200, yeah. Okay, so what does that depend on? The velocity, because nova as well, the white dwarfs are relatively standard. So why would we expect this? I'm not too familiar with stellar astrophysics, but this strong variation.
it's likely due to the white mass, to the mass of the white.
Okay.
So I mentioned that more massive white require this material.
Mhm.
Also, they have a higher escape velocity. So one more massive white dwarf, a similar amount of energy will apply to a less to a thinner layer of material. So they will expand with higher velocity. And because the expansion velocity is the escape velocity, sorry, is higher, the slow material will eventually come back to the So in the end, the velocity of that we record will depend on the mass of the white.
Yeah.
But if but we don't know a proper expression for that. So from this, we can only say that this is more massive than this, likely. But that's it.
Okay. Okay. And for the deceleration, have you checked the dependence on the density of the ISM nearby? I mean, at least based on the observed, the cirrus clouds and the filaments.
Yes. So I didn't check the density itself, but people have been doing that, and they found that
No correlation.
there's no more than no correlation is that it's believed that so people have been found not in this kind of city but in other in regular nova count points that we call points of material. And this happens because the continuous ejections start to close the material, closing a vacuum. So it's expected that the density in this around the system will be a bit lower than in the ISM, in the normal ISM. So again, this could be an explanation why they could continue expanding without signals of deceleration at the time.
Sorry, just one more question to better put this in mind. So what's the distance that in terms of physical distance, like in parsecs? So this would be,
But for example, for RP, we measure the physical size.
yes. Oh, AU. Okay, sorry.
10,000 AU. And this is one of the oldest. So
Yes.
more than the chance to be this case of 10,000 of AU.
And this is after how many years?
Almost 100.
After 100 years, 1,000 years. Thank you.
More questions?
Thank you for the talk. Very interesting to see these results. About the H alpha images with the BSD. This, yeah, it does that you don't find anything with the BSD that you don't find the results.
No, we detect, for example.
You had the MUSE one beside that.
Yeah, the MUSE one.
So here, for example, for this particular, we use this system. We put it in the sample as a head check.
Yeah.
We check if we could detect it and we couldn't. This is bad. In other image, we couldn't detect anything that could relate to a shell. Of course, in those systems that are close to the galactic plane, we detect nebulosity. But we think that they are coming from the interstellar medium more than the announced itself.
Okay.
What is the exposure time here?
Do
you remember?
Usually, so for most image in hydrogen alpha is 1,500 seconds, more or less. It varies, but it's in that order of magnitude.
So omega cam is good when you have when you want a huge field of view.
Yep.
Right, but this is like only 30 arc seconds. So
correct.
why did you choose omega here?
Because we were expecting to find something like this. And
You
we went to
wanted
the schedule
the
7 minutes.
okay, you wanted yes, but then you're zooming into so then because on that scale the surface brightness goes on the much larger area helps in the detection, but the images are showing you're only a few arc seconds. So did you also check on the
Yes.
larger scale of several arc minutes?
Yes, we checked.
And you couldn't find
No, we couldn't find anything like this. As I was saying, we find some nebulosities, for example, so here. But we had to do that to the nebulosities in the stellar medium, not the result of anti-nebulosity.
And what's the width of the H alpha narrow?
106 angstrom.
Oh, okay. Well, yeah, but probably that's the reason. Like if it was a narrower image, a narrow filter.
Yeah, but that is the filter that Omega can have. So we have to work with that.
And then when you look at the image around the star, it's a little white. So in the the next one, the one with the here. So it's been over subtracted a little, but and how did you match the TSFs between the R band and the H alpha?
Oh, but I did it in. So the subtraction I did was first to. So air image is more deeper. It's deeper than the H alpha. So I select stars in the air image and mask them. That's why you see these holes in the image.
Exactly. Yes.
And when I masked the star, so I found a value so that the both images have a common value for the background and the dispersion, and then subtract it using these residuals. I don't know that is the most optimal way to subtract image actually.
So you didn't account for the much wider R band? You must have accounted for that.
No, that is a work in progress because
Okay.
well, in the original work, you only have this one and this one. So I sent this work to the collaborators, and one of them replied that I should start to subtract the R image to the Hallgen.
Yeah, you
So
should
I start
first
to do that.
Okay.
And I started with this one because we know what the shell is. So we couldn't like it, but yes, I have to expand this work to the whole field of view and for all the contents.
Yes.
Although I don't see that I find anything. But I have.
Yeah, here now while you're here, Rehna done a lot of work these days in continuum subtraction with broadband and narrowband. So maybe you guys can talk. Yeah.
So have you checked the UV counterpart of this?
I'm sorry?
UV counterpart for this.
UV?
Counterpart.
If I check the ultraviolets?
Yeah.
No.
She
Actually,
also
this-
has a good database.
Actually, this is a good question because the first ancient shell was actually discovered in ultraviolet. The Shara paper
Ultraviolet, really?
that was a galaxy observation. He found it in a galaxy observation and then followed up in optical.
I will check it.
More questions? But is there an estimate for the typical range in density and temperature during the ejection? So from the first ejecta till the nebular phase? What's the change in density and what's the change in temperature? Or maybe,
I don't know.
but in the at least in the nebular phase, you can measure densities with the sulfur doublet.
Oh yes. No, you just doing the first stage. So yeah, so people have measuring abundance of temperature in this stage. When you still have some sulfur lines and the oxygen lines. In the stage that we are, most of the lines are already not observed. So we cannot do that, but yes, people are doing that and measure temperature densities during the first moments of the eruption.
Do you remember more or less the number?
I don't have the number of mass in the mass ejected. It's always in this order of 10 to the minus 5 solar masses. Abundance, there are always an abundance of the CNO elements by several orders of magnitude compared to the solar. Temperature density, I don't have a number in mind.
Okay.
I was also thinking about what kind of diagnostics can you obtain from this nebula spectrum in this phase. And how this, I was wondering also if this is very far from my field, but if there is a way to simulate the progression of the physical properties of this ejecta with hydro.
So diagnosis, so we can do the basis of nebula diagnosis, temperature and density, by measuring the strength of certain lines.
But for instance, it's similar to H2 regions, for instance, that you can do the ratio between the aurora oxygen fluid
Yeah.
and so it's basically the same.
Basically the same.
Okay.
When it's more in this stage, yes.
So that one is very hot.
Yeah.
The aurora line is huge. Yeah.
But you can do it in the nebular phase. Obviously, you cannot do it before.
Of course. Yeah.
The second question, simulations about how to eject material. To my mind, there is no questions. There is one, the 1998, that showed how the ejector behaves regarding the spin of the white dwarf.
Mhm.
So they simulate how the spin of the white dwarf affects the electron.
Okay.
But that was 20 years ago. Since then, I don't have another work on mine regarding simulations of the ejector.
There's a couple of groups working on this. One is actually here. Well, there. One is the Barcelona group, Jordi Jose and others. Jordi together with Mike, Steve Shore, and then there's the other groups in the US like Samna, Starfield, and it's basically.
Yes, but they, for example, Starfield or someone, or I don't know. I haven't checked the work of the Hillman, maybe you can also see. They also simulate, but the effect of the eruption in the white dwarf, and once they eject the material, they forget about that.
Jordi for sure is more in the direction of what Ricardo was asking. I'm pretty sure that Samner is also. Yeah, that's for sure. Yeah, it is mostly the effect on the white dwarf.
The nebular phase appears like 1 year after the explosion.
Yes.
Month.
So
1 month?
This is the nebular phase. At this point was here to start to appear something like So yeah, months after
The thing is, basically any nova is a different universe. Easily you can start having a nebular phase a month after the maximum, or a few weeks after maximum.
1 month you start to see the H alpha, but
No.
the
H alpha is right away.
okay.
I'm speaking about nebular phase when you can.
But you're speaking about the forbidden transitions
the third plot.
or the
The
third plot.
there.
So the third plot you see it already 1 month after the
Depending on the nova,
Yeah,
you
yeah,
can
yeah.
see it. Yeah,
more or less. That's the
1 or 2
timescale.
months after the outburst.
We also divide the nova, or depending on how fast they evolve. For example, this one is evolve faster because small decline and start to increase faster. But this one not. So we start here a while and then become this one. So in this case, we start to evolve later. Yeah, you will see this phase would be 1 year later. But in the first one, I don't know, maybe 1, 2 months after.
Yeah, it also depends if the source is still ionizing the material, maybe you don't see it until it recombines. So, but just to know the typical timescale. Because the density has to change by a lot, because you don't see the forbidden transitions at the earliest plot. That means that densities are about 10 to the 7, no? More or less, or
I never remember the numbers.
but like
I don't remember this, but
then in the lower ones, let's assume I don't know the sulfur doublet, but the densities will be of around, in the third plot, not larger than 10 to the 4, I guess. And probably lower, so that means that it expands and it changes the density by a lot.
The velocity, the typical, actually you have it on the plot on the right. The typical expansion velocity is just, we are speaking about hundreds, if not 1,500 kilometers a second. And a typical P-Cygni profile, this actually is slow, but a typical P-Cygni profile would be about 500, 1,000 kilometers a second. This one is on the slow side. It doesn't even reach 500 kilometers a second.
Okay, more questions? If not, let's thank Lientur again.
Thank you. And I suppose, according to the Fueros de Aragon, we're supposed to bring the speaker to lunch.
Probably, no? It's Friday, so
It's Friday.
there is no escape.
He's forced to join for lunch. Linda, are you there?
Yeah.